That'll do it.
So.
Nice.
So, I don't know if I'm already streaming here, or I don't know. Can somebody go to a YouTube link and check if it works? So it's you just type in watch !v. Okay. Is here?
Hold on, I need to connect to
It's work.
Yeah.
Is that fee?
Yeah.
I don't know what this is. It's actually.
Which one should I? Which?
It's DEFCON.
DEFCON 5. Okay.
Okay, it works.
Well, DEFCON is the best one.
No,
No.
but welcome to Berlin.
Yeah.
Okay.
One word. Oh, yeah.
On my computer already.
So can you try typing this?
Okay.
One of them lets you down. Another one.
And Wi-Fi password.
Okay.
What's the Wi-Fi password?
Welcome to Berlin. One word all the way, please.
Yeah. Oh, one should disable proxy settings. Trying to do this.
Always fun.
Yes. I always actually have a faster way to do this.
Okay. You should then. So you see, there's a little delayed,
Yeah.
but that's cool. Okay.
So all set. Okay. There we go. Cool. I think it was proxying like half of the functions. So she did that.
Okay. Okay, so you want to stand here or
Yeah.
figure out how I position this computer so that everybody.
Yeah, that'll work. Rant to people about things they already know.
Okay.
Cool. You pick the thing to start with. All right. I don't know how many people are.
Three.
3 people. Cool. Hello, people.
Okay. We're gonna move it a little back.
There we go. That's cool.
Okay.
Hello, people that I don't know who are watching. This will be a very, very fast introduction to what IPFS is, how it works, what the layering is, what the model is, and then we'll dive into formats and linking and how it might work with Ethereum and so on. Cool. And then really whatever people want to discuss. I'm down to talk about anything. We can draw on things. If people want to demo cool stuff as well, like, that'd be great. I know Chris has like this really cool data structure that he made. I start with this because it's like the web started over here in the notion of being completely distributed and peer-to-peer, and it totally moved towards a centralized thing. And I think we'll agree that it needs to go back to being much more distributed. But the key problem is that everything is location addressed in HTTP, and moving to content addressing is what helps remove that issue. And it's not just content addressing, it's content addressing and identity addressing, meaning that you can address something by the identity that created it. So the hashable public key and so on. I think we're all, anyone need me to explain content addressing? Nope, cool, no, awesome. So we can like just go through all of this. I'll just like skip through that. Great. So basically you have paths in IPFS that look like that, where you have a domain. This that doesn't necessarily need to be DNS, it can be something else. But you have some pre-named resolver. There's an extra step in here where it maps to the hash of a public key, and then it maps the hash of the content. And so you have a URL that has resolution on content itself. And this is a Merkle tree. So the content that you access from a hash gives you an object. It has links that are also Merkle links that link to other objects. And that way you can traverse a graph. Right? So this is kind of accessing a graph. I could just as easily access something like by the hash of foo, and then go hash of foo /bar/baz, or like really go all the way to just /IPFS/ the hash of this last part. Is that kind of?
Yeah, where you store that information of the path?
So the path is in the actual object. So let me sink into that in a moment. So yeah, let me skip this part. I'll return to this in a moment. So the model of IPFS has two things. One is the Merkle lab, or really Merkle lab. You need to find a good name for it, but it's this notion of linking all content with Merkle, with a Merkle tree. And it has IPFS nodes. IPFS nodes are just processes that move around content running the IPFS protocol. So these are designed to be extremely ubiquitous. So there's no decision that we've made that blocks out any kind of platform or architecture or anything from implementing this protocol. So you could see it embedded into like various small low-power devices. You could see it embedded into Internet of Things. You could see it embedded into applications that are running. You could see it embedded into web applications running in JavaScript. And so the whole point is to make that as deployable as possible. In the same way that HTTP is as deployable as possible, right? You can basically do an HTTP request from almost anything. And we need that level of ubiquity. Any questions on that? Because that usually raises a lot of questions about like transports and routing and so on.
Well, yeah, I don't want to derail you, but
Cool. Yeah, I'll go back to that routing. Routing is a big deal. I say to the person who wears the Tor. So content and programs, and so the content is this huge graph where all of the edges are Merkle links, meaning a hash of the content. And so it kind of looks like this, right? So you have this graph, and you might have these this link table, and here we have three different objects. We're looking into three nodes. The first node has no data, and it has three links. The very first part is a hash. The second part is a size. That size is the cumulative size of all the children on that path. This is used for replication because that way you can know how much you're about to fetch. And the last part is a name, and that's meant to be human readable and displayable in both Unix and the web. So that is an explicit choice to make sure that all of this stuff can be mounted both in the file system of a regular computer today and on the web as it is today without any modification. That is a much bigger deal than people, like, I guess, mostly realize, because tons of systems out there create universes of stuff that isn't easily expressed on the web or the file system. And if you don't do both, then you've now you created this rift. You've deepened the rift between Unix and the web. Cool. And so the second object here has a link and some data, right? So 1 points to 2 through the foo link, say, and 2 points to 3 through its diff link, and the last one has some data, but no links. So it's a leaf. Straightforward.
So the orange one is diff.
The orange one. So let's resolve real quick, right? So suppose that the hash of one is QMW whatever. So if we resolve /IPFS/QMW98, we get 1. If we resolve that /foo, we get 2. If we resolve that /bar, we get 3 because QMW98 pulls out 1, and then under that we resolve bar, and so we end up with 3. Is that clear? Right.
Why is bar the orange one?
So we start with
QMW, okay.
Yeah, so we start with this hash, and this hash pulls out. We assume that this hash is 1. So we pull out 1, and under it we look at bar, and so we look at 1 and we look at its bar link, and then that link is that hash over there, and so we pull that out.
Yeah, but it's flu.
What's that?
The QMBTQM is flu.
Oh, so no, that's the link from 2 to 3.
Ah, all right, okay.
So both 1 and 2 point to 3. So that's why QMBTQ appears.
So it's just the link, it's not the content.
Right. It's just 1. So this is why it's yeah, I'll talk about that a little bit more in a second. But you get bar, right? So you can also resolve 3 as /foo/diff. Right? Because in /foo we pull out 1, we go down the foo edge to 2, and there we ask for diff, which is the only link, and we get to 3. Sound good? This is like just standard file system resolution, but it's done with Merkle links, which means that the entire data structure is authenticated. Cool. And these objects don't necessarily have to be like this. Feels like a directory, right? Like navigating a directory. So number 1 feels like a directory because it has links and names, kind of like an inode or a app name. And number 3 feels like a file because it has data. But 2 is somewhere in between. It has both a link and some data. And the realization there is that perhaps directories and files could be the same thing, as the web points out. In the web, you have a path name, and a path name could be both content, and it could have content within it. Right? So if you go to example.com/foo, that could be a web page, and it itself could be. You could have another web page at example.com/foo/bar. And the idea there is that every single path could be resolvable for its data, and at the same time have links to deeper things, which gives you this enormous flexibility because you can model anything.
Then you can't map that to the file system anymore.
You can't map everything to the file system that way. No. So some things you'll have to make some compromises on how you express it to the file system.
But once you distributed the right link system, you can basically just host any website, browse it through like a normal website.
Yep.
And this runs over HTTP or?
So we happen to use an HTTP server locally, localhost, but it runs. We have our own transport, which is IPFS. So in a sense, IPFS is a data structure transport. It is a protocol designed to move around this Merkle linked data structure and the additional layer of immutable names that I haven't discussed yet. Cool. Any other questions so far? I'm trying to play through a lot of this, and I don't want to lose anybody. But your point, you can model Unix files and directories on top of this, but as you pointed out, if you go into the file system, you can't cat a directory, and you can't OS a file, right? The way we get around that is that we get around that in 2 ways. One way is that the very core data structure is a very flexible substrate that you can use to build other data structures. For example, like Unix files and directories. So you could take one of these nodes and put only links in it and no data and call that a directory. Or you could put data in it and no links and call that a Unix file. And so you can map a regular Unix file system onto this. You could go further and say, just look at that in a moment, but you could take a big file and chunk it into a whole bunch of pieces and create a whole bunch of set of different nodes and let the file be the concatenation of all the data. But then, now we're talking about like a different mounting, right? So the way we get around that is that you can, one way is to mount, you could mount two file systems, one which just gives you access to the raw data of the objects, which in this case would like pump out like the raw description of the links and the data, and everything would be a file. Another option would be to define on each object what it means for it to have data. And in the case of Unix file systems, we do this sort of a hack where we create a data structure called UnixFS that has files and directories that expose the normal semantics that people might be familiar with in terms of directories are listable, files are catable, but the other one isn't. Does that sort of address the point? It is an annoying thing we have to deal with because some things aren't as easily mountable into the file system. We have to do some hacks, like perhaps express. So the way the web does it is that the web says that the index.html file is the content of the directory, sort of. It has like this weird hack. And so we can do things like that too.
It also doesn't expose a way to list a directory to the client. There's not a standard directory listing.
Like in the very beginning, there was where like it would generate like a listing of the files inside of it, but then that went away because that's, you don't want just to list random things. But we can do things like that in the file system. So when we mount, we get to define special objects, for example, that might represent the data within a directory and a special name, for example, like dot data or something. Of course, at that point, you're shooting yourself in the foot because you might want to use that name for something else. So you have to be careful, but that is available to us if we need it. But you don't just represent Unix files and directories. You can represent anything, right? Like you can represent Git. Git is the same thing. Git is just a blob, which is data. You have a tree, which is a directory. And you have a commit object, which is neither of those things, but it has both links and data. But you can create objects on IPFS that represent each one of those things, and you now have Git writing on IPFS. So for each one of the Git objects, you would have you could run an import command that would import all of the objects into IPFS, and it would just go and wrap all of them with the IPFS link table. Does that kind of make sense? I might have, yeah.
If you have links and optional content on an object, how do you specify its type? I mean, these are kind of types, right?
Yes.
Stream, comment, file, UnixFS.
Typing is a really hard question.
Or just the client or the node reading this stuff just assume something?
Yeah, so for now, the way we've gotten away with it so far is that when you receive a hash, you can do two things. One, you can look at it and try to decipher the data, which is not ideal. And the other is you are given it in a context, and because you're given it in a context, you assume it is of a certain type. Neither of those is ideal, and we are going to find a solid typing system. It's just that is one of those decisions that is so hard to make right that we wanted to really think carefully about this. It looks like what we'll probably do, and we may change our minds tomorrow, but it looks like what we'll probably do is follow something like what JSON LD does. So the semantic web is this awesome, amazing thing that Tim Berners-Lee and a whole bunch of other people came up with that's extremely powerful. However, it has a set of problems, including like formats that people don't want to use, and it has like latency and bandwidth problems, because when you look at standard semantic data, semantic web data, to run like a Sparkle query through something, you have to touch tons of different machines, right? So it ends up being pretty slow. And then people try to work around that with like various hacks, but it's not all properly implemented, and it's kind of a mess. For the most part, it sort of works. I mean, you certainly don't see like major websites doing this, right? now you sort of see it with Facebook doing Open Graph because they want to own a ton of that information. Open Graph. And the Google Knowledge Graph, which is both of these are like corporate moves to make the semantic web in-house because they realize how valuable it is to do that. And they said, oh my God, we have to make this, and it's going to be amazing. And we're going to own it all. And we're going to let people resolve queries over it, but that's it. None of it is actually available, really. There's some subsets that are available. So I recently found out that if some subsets of Facebook are actually available in like Turtle, they'll give you like RDF or proper Turtle, and you can sort of claim that it's open.
After registration.
Right. But several problems have been solved in the semantic web world. One of them is the formats thing. So recently, JSON-LD is this really nice format that said, keep your APIs as you have them, use JSON because you like it and it's nice and you already built it that way. Add one key that points to a context file, and now you have the full power of the semantic web. It's a really elegant solution. Another problem that we might be solving is the latency bandwidth query problem, because if we make all these specs content addressable, then we can just pull them and bundle them and deliver them. And more so if they get signed, right? So when you give a linked data application to somebody, it would carry in with it all the specs, so there's no extra performance hit. So this might be an interesting direction to go in. I hesitate always with saying we're going to go like the linked data route because it usually is like a mountain of problems, and it does give you a lot of power, but it is difficult. But it seems like the JSON-LD route is pretty safe, so we'll probably add typing that way. Yeah, does that kind of elucidate like the decision making here? Cool. Any other questions on typing or these subjects? Yeah. Cool. You can also do blockchains, right? You can take a big data structure like a blockchain and all the blocks, the transactions, and the wallets, and so on, and model it as this huge Merkle diagram, because it is, and just import it into IPFS. And once you import it into IPFS, then you can move around in the same way as all the other content. It can be viewed through the same set of tools that we're making, and I'll show you some of those, and so on. You can model key value stores. You can model like pretty much anything. You can model databases that are sort of open, right? So today in the web, you have all these front faces of websites that you talk to, and the website has this big database underneath, behind the scenes. And IPFS allows you to just flip that and put the data outside and just compute on the data itself. So you can have code in your client that is manipulating the data. And if you use things like CRDTs, then this makes a lot of sense, right? Because then you can do convergent changes to data, and that means you can do offline websites, right? So the vision here is going from a world where you have these monolithic websites that give you sort of like a storefront and you access everything to that, to a world where the actual web, not native applications that happen to use HTTP, but rather the entire web delivers a web app payload to your machine, and you run it, you can cache it forever. You can be disconnected from the backbone and run it. Or you can run it with peers locally and that kind of stuff. So that's where we're headed. And we actually have a lot of that working. We already deliver the web UI front end for IPFS is an application like this, and you can continue to run it when you're offline. Cool. So yeah, here's where like explain that how the UnixFS thing works. Here's paths. I kind of went over this, but just to give you a quick notion of the resolution, the blue link, blue object, pulling out, right? That kind of makes sense. Here's how you would model a blockchain, where you have like some block, you have a parent hash that points to the previous parent, you point to some like transactions perhaps, and you have like some number, and here you can see the inputs and outputs or whatever, right? And all of these objects could be thrown onto the web, which means that other things that are not blockchains could point to them, right? So you could have a git commit that says, as this thing fixes some bug as was shown in transaction whatever, and then it would make a link to that transaction. And now you have the two data structures linked. Or likewise, here you could have like, I am paying so-and-so because of commit block, and it would link to the actual commit. And IPFS would understand how the entire data structure is linked and move those objects around together. Another example is if you had a chat application and you're messaging and you include like a link to an image that is an IPFS, then that chat message would include the attachment of an image. And so you could decide when you're replicating the feed whether to replicate just the messages or the entire content. And so when your application just downloads everything and caches it forever.
So in the case of like putting the Bitcoin blockchain on there, if you want to store a transaction, you store the entire history of transactions from when that transaction's coins were minted, but not the whole blockchain.
You can put the entire blockchain on.
I mean, you could do that too, but you could also just using the IPFS
Yeah.
structure, you get the path back to the coins being minted.
Yep. Yeah, you would have this enormous path following parent all the way back, right? And you can, even if you don't want to express this massive like path, you can just pull out the objects and resolve through them and explore the graph. And then you get the power of then linking that to other data structures that are around that may not be on the same system, which is useful. Cool. Other questions on that? Cool. Merkle bag because the links are hashes. Great. I think the other thing to talk about would be routing, which I think is important a little bit. Just really quickly, an IPFS node has a public private key pair, connects to other nodes, stores part of the DAG, moves it around, maybe around the server, or embedded in applications, and or peer-to-peer networks, and so on. All right, routing. So a lot of this design points out that when you actually want to move around content and exchange content with other peers, you have to answer two questions. One is, where is the content? And once you receive identities of people that have that content, is how do I get in touch with those people? So the BitTorrent DHT solves this problem, right? You take an info hash and you resolve it to a torrent, to a group of people that have that hash, that has that torrent, and then you find the addresses of those people and connect to them, and now you can start moving around content. Those two questions are fundamental to both performance and privacy, because how you make those accesses is what it defines whether or not your transaction is actually like going to be fast or going to be secure or quick. Because you might opt to say, I just want this content right now, and I don't care who knows about me requesting this content, and I could be pulling it from another computer in the same room, and ideally, like that will happen. And in that case, you might be fine advertising to the rest of the local network that you want that content. But that is a trade-off in privacy, right? You have now told the other people in the network, some of which you may not know, that you're looking for some piece of content. On the converse, some content you may not want to publicly advertise that you're reviewing, right? Like if you're part of like the Egyptian rebel group and you're moving around like important information about where they're like, located or whatever, you don't want to just broadcast to your local network or whatever the location of those things. And so how you talk to other nodes is what defines how you should pull in the content, and has strong bearing on the guarantees, both on performance and on privacy. And so we sync all of those problems into the choice of routing system. And so a standard default of a choice of routing system would be a DHT, but that has privacy problems, right? Like you don't want to just store random things in a DHT that has privacy implications. You could do something even more high performance, like do local DNS, and we do that. You can advertise and pull in content from the local network, but that also has some problems. On the other side, you could route all the content to Tor, or even not even know who has what content, but rather do queries for content and retrieve them through relays without ever knowing exactly who's giving you the thing. And that is privacy preserving, but it's not going to be very fast. And so people's web usage usually falls into these two types of buckets, where sometimes you want your Minecraft game to go really, really fast, and sometimes you want your private email to like not be broadcast to people, or like people not know who you're messaging with or whatever, right? Does that sort of jive well with people's notions of traffic? Usually everyone immediately is like, no, like this and that. So yeah.
Which of these routing mechanisms you mentioned are?
So right now we have a canary DHT and we have local DNS. Local DNS is still halfway there in that it helps bootstrap to other people, but it doesn't yet. You don't yet do actual routing queries like who has what in there. That would be ideal for when you're in a room full of like 100 people. Like that would be really nice.
Just to clarify, when you say routing, you mean locating
content? Yes. So not routing packets, right?
But resolving content to
yes.
your location.
Yes. So it's content and identity resolution. So resolving who has what and resolving where they are, which changes, right? So my laptop right now is here and has a set of addresses, and an hour ago it was elsewhere and had a different set of addresses, and now the network has to be updated on this. And so if people want to retrieve content from their laptop, they have to be aware of this. And the network is really messy. People have different addresses. You have to deal with this. Is only going to get worse with the Internet of Things as small devices emerge.
I'm curious what your Tor routing, where you don't know who has what, sounds like some private information retrieval, and that raises all sorts of questions about how you think you could do that.
Yeah, like who is actually requesting this thing, and how are they making that request?
Yeah, but also I'm not at all convinced that the DHT model can't actually be made a bit more private than it typically is
Yeah,
I want to be right
agree.
again, but
I actually agree.
it can actually be private and fast. I'm pretty sure there's a way to not have to have a trade-off that's too huge.
Yeah, it depends on what we mean by fast, right? So if we want fast to not hit the backbone, like that's going to be really hard with privacy preserving. Depending on so this boils down to how much work you've done up front in terms of building knowledge of what other peers are around you and how much you trust them and what you're resolving to them and so on. But yeah, there actually are a lot of DHT-like things that are much more privacy preserving. I don't think any of them have been implemented yet. They're papers, but yeah, would be cool. So you might notice that I had at the very beginning, as I blaze through all of this stack. Oh my God, no, you don't. This stack. So this is a set of sort of technologies that, in a sense, roughly correlate with our stack, in that there's routing, there's like exchanging of data, there's modeling of data, there's naming, haven't really talked about naming, and there's actual web of content and moving around applications entirely. So at the very bottom we have network, which is just being able to find each other and do map whole bunch of routing is a little bit of that in terms of finding each other, but primarily it's about content. And this is swappable. So like I was saying, you can have a DHT, but you could replace it with something else in the future, right? So, and you might actually have multiple routing systems. So instead of just using one, you might have a node or multiple nodes that use different routing systems, depending on the content that you're writing through them. Or depending on the network, you might actually have an organization that has its own routing system, or you might have a data center that has its routing system just be a single file with all of the content, because that's super fast. And like right away, everyone knows where everything is. And so that's totally fine, that's totally possible. And it should be pluggable. And so what you want to do is make sure that everything else can work with that as a layer that gets swapped. So we want to define these interfaces very carefully. our exchange thing is a thing called BitSwap, which is a generalized BitTorrent type of thing that is going to make it possible for agents to do more interesting things than just tit for tat, and rather do more expressive notions of transactions. It's still peer-to-peer, but those transactions might actually express, oh, actually give me some cryptocurrency, so I'm gonna wait before I send you something until some transaction happens, or a microtransaction channel type of stuff, or that sort of thing. I can expand on that, but that's like a whole topic in itself. May not be that interesting now. Cool. So yeah, this IPFS is really about the way we structure content, the names, and then layering on these other pieces. Ideally, we never would have had to build this, right? This would have just happened for us, but the world is not that nice. And so we had to scope them out. And we are starting with a Kademlia style DHT, but we're going to move to something better in the future. Yeah. Any questions on this? Cool. Where are people at? What are you interested in?
Examples.
Examples. Cool. Demo?
Demo.
Like an actual demo? Or like what kind of examples?
Yeah, demo. Cool.
Let's do it. Although I'm kind of bored. Some people have seen this before. So here have IPFS running. It's a daemon. You're probably not going to be able to see it.
Yeah, I moved it a little in front, so maybe it's possible to see this then.
Yeah, so for now, the main IPFS distribution is a command line tool that you run locally. But in the future, we'll have implementations of JavaScript that you can run directly on the browser. You can embed IPFS as a library into your application, so you don't need to use it as a separate binary. But for now, this is like the simplest way to use it, and you can think of it kind of like Git. And so, to give you, here, I'll just blow out my.
Can you make it a little bigger?
Yeah. Kind of a lot of stuff in there. Goodbye. I don't even know what's in it. So when you initialize node, you generate some key pair. For now, as I say, we're going to move to ECC. And you are greeted by this message that says you have some peer identity. This is the hash of your public key. And you can pull out some file. And so if you run this command, this might actually blur out because we have it blurred recently.
Why does everything start with QM?
Aha, great question. Because we want to be able to evolve our hashes. So we used to have a format called multi-hash. So let's see if this will. We use a format called multi-hash that just has at the very beginning a code for a function, then the size of the actual digits, and then the hash digits. And the reasoning here is that if we need to move from SHA-1, which is already broken, and I use it here as an example of something you want to move away from, but instead move to SHA-2, then you can use them safely in your system and know that in the future you can upgrade, right? So you don't tie yourself to SHA-2.
What is how does the QM resolve?
So there's a table that we agree on.
Okay. And
Yeah, so there's like a table here. Yeah, so QM, so when you do take like hex 12 and then move it to base 58, you get QM.
Okay.
It's not just the 12, it's also the length.
The hash. Okay.
Yeah, so here,
I see.
I have this handy tool called multi-hash, so I can echo foo into multi-hash. And this gives me this thing, I can encode it into hex. D? Yeah, D works. So that's the hex output. And so I can say an algorithm of SHA-1 instead, or SHA-2, 256, or SHA-2, 512, SHA-3. And then I can actually specify the length. Maybe I want to put it and say, 256 bits. So it's SHA-3, but it's like 256 bits. And the reason for doing that is that if you have these two hashes and they're the same length, like actually knowing that this is a SHA-3 that's been clipped is really valuable information for you to know. Because for example, SHA-2, 56, and 512 get used in different applications because they'll start with SHA-56, but then they'll realize that 512 is faster on some architectures. So somebody will be like, and switch it, and will not document it properly. And then suddenly hashes won't match between implementations of things, and people will freak out. And this is because people didn't clarify in the hash results what the actual function used to generate hash was. So this is also a problem because people assume the length of the hashes, right? So everybody who's written a Git tool will assume that a Git commit has a specific SHA-1 value and will generally look for things that have, if it's printed, 40 bytes, right? It's like a hex output. So they'll correct for that. And so if Git were to change from SHA-1 to SHA-6 today, they would have to flip it to 160 or break tons of tools, which is a pain, right? So this is why we use this format. We have a similar format called multi-adder, and you can guess what it does. If we show the peers that we have here, which are the peer that I connected to with my episode, it's smaller a little bit. You can see that there's a multi-adder that starts with IPv4, gives me an IP address, TCP, the port, and then IPFS protocol, and then the ID. And the part of the point here is that then you can become properly transport agnostic. Because if you want to add support for UDP, or like UDP over UDP, it becomes just build it into the protocol and then specify a different address that is just slightly longer because it expresses it in there what's going on. If you want to give your entire node an IPv6 address and that's it, and no like nothing else, you can do that and just drop out the transport part.
So how do IPv4 nodes reach you if you're IPv6 only?
In that case, IPv4. So if your application only had an IPv6 address, they couldn't. They would have to relay over somebody else.
So but they could relay over somebody else.
Yeah, they could.
So there's relaying is already
there is relay. So it's not shipped at the moment. It's there. The code works. That is a big thing to have happen. We want to do it in a way that we can select who's relaying and have some way of incentivizing relaying. That would be the ideal way of doing this.
Mm-hmm.
So that you have dedicated relays that are pretty powerful. Part of the point here, though, is that necessarily in the network, you will have nodes that can't speak to each other. So for example, a node inside of a browser tab will probably not be able to talk to your watch because your watch is probably not going to be running WebRTC or WebSocket or running an HTTP server anytime soon. They might in the future, but like not at the moment. And your browser is not going to be able to like dial a HTTP socket. They have to only do WebSockets or WebRTC. So they can't actually talk directly. You would have to route with something else. Or if you have something that's like connected over Bluetooth, right? And so the internet has many different transports. We need to like deal with it and then route our protocols on top of whatever those transports are.
Which means adding relay,
Yes, which needs to be done. And so one of the things though is that depending on how relaying is done, you could have a system where people have to find themselves a relay. As in order for me to be reached, I have to set some set of dedicated relays. Versus blanket telling everyone, you will get a relay people's traffic. We don't want to do that because some people will be running IPFS nodes that don't want to store other people's data and don't want to relay other people's stuff, period. And so we have to find a way in the middle where it is possible for relay to happen, but it's not mandated on everyone.
I have a bunch of ideas in that area, but I don't want to derail your.
Sure. Cool. So anyway, this is the number of like I have right now my IPFS node. I started at the beginning, which means that it is running a couple of servers here, and it is also talking to other nodes. And so it's this is the list of nodes that it's connected to. I can show you like a web UI. And so this is like what it looks like. Hey, what you found it. This is not the new one yet. The one that's like another. And here you can see like nodes that's connected. So this is like management of my own node. And if you notice, this entire website, so it is hosted on a hash, which means that the whole thing is delivered through IPFS. So I can actually disconnect from the network right now and refresh this page, and it should work. It's not going to work. What? This is making sense.
The content ID in the URL is your peer's public key, right?
Yeah.
Or
How
hash.
does this like not actually working? Yes, that's
And
correct.
I noticed it's a longer hash than the ones previously in the presentation.
Maybe you're trying to access IPv6.
I think what happened was that my node got closed somehow. Or it didn't have the entire thing. That's also possible. Oh, I know what happened. This was cached. This is Chrome, this Chrome thing. You'll see. I'll go back online and I'll do it on a creative. And the first time it'll be slow. So
Right. You deleted your IPFS.
yeah, so right now I'm not connected to anything. So this one again.
Something's
Oh, I may not be in the right network. If I want to Palantir, I'm not in the right network. Yep. All right, back to the original network. So it's organized. So I gotta go do software. Cool. So visualizing. Right now it's bootstrapping this letter here, so now it's bootstrapped, and it's gonna start finding more. Now when I go to this web UI, it's going to take a while to load it. So yeah, see, not crazy. So now, now it loaded it. Now it's here on this node. So we can verify that because we can take the hash and say, yeah, IPFS, show me all the refs that this hash points to. It's like listing them out. So it hasn't even done all of them. But it's like, okay. It should be a lot faster. That's weird. What is, I'm curious, what is like the network speed here? Because I'm always like slugging.
sometimes it gets slow.
Okay.
I mean, sometimes it's 10 meg up and down, and sometimes it's
Awfully
Okay.
slow.
Okay, so it is not like this super fast, like 100 megabit per second line with like the spotless or
That's a pretty good
line.
difference.
Okay. Cool. So now I have that whole thing here. So now I can do the whole disconnecting from the network and refreshing this page. So yeah, disconnected, refresh the page, and set. If I go to connections, I'm connecting to OT. And if I turn on this Wi-Fi network, I'm connected to the right network, then it will, as it starts connecting to OT. So it'll take a bit of time. Well, that was pretty fast. That was really fast. What happened there is that other people may have been trying to dial me, and so when I connected, I received all those incoming connections. And so that is a running website on IPFS delivered through the node working offline.
So in this case, you have everything with relative path because you have folder structure already from.
Yes. Yeah, so the content that's here is either pointing to other IPFS hashes, which are basically like dominant. Like you get relative pathing out of how the Merkle DAG works. Remember that format that we had? If you link all the things
So
together.
if I'm putting in a hash, how does the browser now know how to resolve it?
So if you see that there's this localhost part here.
Yeah.
So this is right now a hack to make, so the node that's running in the binary happens to open an HTTP gateway.
Okay, so you're writing HTTP / then the hash of the website / some path.
Right.
/ some other hash.
Right. So you can actually exchange this for gateway.ipfs.io. It's not gonna it's not gonna load nicely. It's not gonna have access to the API. But I'll show you that. We'll actually load the content. Yeah. So this is like it loaded the assets. It doesn't have access to the API, so it doesn't show me anything. But this is at a different domain, right? So this is a public gateway that we run. So that, for example, if I were to add content here, say like like echo foo pipe into IPFS add. So I get a hash. I can cat that. So I get foo. And I can go to localhost 8080/IPFS/that hash. I get foo. So now the kicker is when I go to gateway.ipfs.io, because this is going to hit a different web server who's going to use IPFS to find the content in my machine and then pull it out. Cool. So that's pretty fast.
Wow, that was fast. So what just happened there? It used the to find your node, but you're behind that here, presumably, right?
Yeah.
So there was some relaying then, or you connected it?
No. So it either found a way to bust a hole in that, or it might have already been connected to me. Happened to get lucky. More likely, it found a hole.
The router here has PNP support.
So we open, yeah. So we use
PNP support.
we try UPnP and NetPnP to open holes, and we do a little bit of smart addressing where we do this whole thing of reusing the TCP port, like, which created a nightmare of other problems. But that means that when we dial out, we're dialing out from the same port that we're listening, which means that other people can dial on the same.
Right.
So, by definition, we're punching a hole ourselves.
But that's not
Guaranteed. It's not guaranteed.
Yeah.
Always.
But if you can connect out,
Yeah.
use the connection to
So if the NAT here wasn't, they didn't have UPnP.
If it was like a
you
semantic
had
NAT,
what?
if it was a semantic NAT where like there was no hole punching possible, then you have to do it.
And then, and if you weren't connected to the
Then it would
gateway,
have just like, yeah. And we can simulate that. Well, actually, it'll be cached in the gateway now. I was gonna say like, here I can add another. Here I can just resolve some like random cache. So like, it doesn't do this. So this is like just gonna hang for a while. You can do it in a separate page. It's gonna hang for a while and then tell you like routing. Like I couldn't find it.
So one question is the IPFS website. Does do the routing in JavaScript, or do you just like point to files?
Does it do the writing in JavaScript or point files? What do you mean?
Can you open this website again? This first one?
So this one?
the
The other one, the web
This one?
website.
Yeah, cool. So,
It basically just loads, so no matter where you route, you don't add anything to the path, you do it through any routing, right? Any routing in the client side.
right, so those paths are retrieved. So I'm fetching content from the node, and the node is figuring out where to get the content from. But once I've got it, that's it. I'm done.
For example, if you click on the left side of this menu.
Yeah.
Okay, you use hashes.
Yeah, so that's, I mean, we could get away with some other structure, but right now we use hashes. And you can actually inspect like the node. So this is like a web UI. So this is like a index.html. You can look at it. It's there. And so on.
And it does have there.
What's that?
it's pretty meta.
Yeah. Okay.
And it does have relative links in there, right?
Yes, it does use relative links here. It is a well-structured website.
So that foo thing you just made, presumably somebody's made foo before. So actually that was probably already on the net. Because it's the string foo new
Give
line.
me some randomness.
Well, no, I don't need to.
Well, no,
Well, let's just say that it's yeah. So that's now an object that's in your node on your laptop, and you're broadcasting to the DHT that you have that.
So by default, right now we do that. Later on, we're going to add the ability to specify content that you do not want to broadcast out to the rest of the network. So there's 3 layers to this. One is, or not layers, but there's 3 main things to care about. One is, do you care to keep the content? Do you want to pin it locally or not?
And when you add it like that, it's not pinned, right?
Right now, when I add it, it doesn't.
Ah.
So when you, because from a UX standpoint, if I specifically add something, I probably want to keep it.
Right.
If I look at something, I probably don't want to keep it.
And how about plausible deniability? So do I store the whole content of other people? So
No, you don't store anything except the company you have requested specifically.
But I relay them.
But you what?
I relay them.
So you might be relaying encrypted traffic that you don't look at. you can't fit it. So you're acting like a router in a regular form. So you really only pull, because you don't want people to be pulling down content that they didn't request, because that might, unless they explicitly are putting themselves up as a service of saying, I am a file hosting service, please deposit your files here and give me money. And like, if that's a different deal than I'm browsing the web. If I'm browsing the web, I don't want to store like evil stuff, right? Where evil stuff is defined by different jurisdictions across the world, right? So it's like, you don't
It's
want
not
to,
before there's some good PIR.
right? So let's start resolving this and see what happens. It works. I'll take a little longer. It works. And to give you a notion of how content is added, like have this demo folder, have this basic thing, and add everything, this thing. So that created like this graph. And show you the graph because that comes out dot output.
So does an add implicate commit or push or
publish? Add right now is a porcelain command that says take all this content, create objects out of it, pin them, and broadcast them to them.
And
Or
broadcast
not
means-
porcelain content, but broadcast to the network that I have them and I'm going to serve them. So as I was saying, there's three things you care about. You care about whether you have it, like you pin it locally. You care about whether you advertise it to the rest of the network, and you care. What was the thing?
And do you also store it on another DHT nodes, or do you only store it on the
Right now, it's only stored. So the point here is that you only use the DHT to do routing.
Yeah. Okay.
So
And somebody requests it, and eventually ends up at your local node, fetches it, also stores it.
Yeah.
Okay.
And how does how does the browser know what kind of content the files are? Is this stored like in these packages, reference by hash?
Yeah, so I can show you the actual raw data, right? So let's look at that for a second. I want to show you also.
So you're wrapping this, right? So you're wrapping the content inside some kind of package of metadata.
Object is a plumbing command. So as in Git, we have these like plumbing commands that are low level, and sportsline commands that do a whole bunch of stuff all at once. Git commit is a beast of a command that does a whole bunch of stuff. Creates a commit, it, like, mutates objects, does a lot of things. And so IPFS add as well does a lot of stuff. But IPFS object can show you like the raw thing. So here's where the raw thing is. So we're rendering it in JSON. Normally it's protocol, but you can actually get that if you want to. So that's the protocol.
How does, for example, the browser know what to do with it? I mean, in this case, it's just text, right?
So in this case, what happened is that when you resolve this object, this data. So right now we're kind of blessing the Unix attest data structure a little bit and saying that we're gonna, when we find Unix attest data structure objects, we're gonna take the data segment and we're gonna take the object and try to render it as it needs to be rendered. Meaning, if it's a file that is made up of a whole bunch of different like nodes, we're gonna dump out all of their data segments and concatenate it. I can give you an example in a second. But this extra stuff is gonna get clipped out, and only the data is gonna pop out.
Okay, so this local node you're running, it delivers on the end the content to the browser
Yes.
with headers, obviously, right?
No, so when it delivers HTTP headers, but it does not. It strips all the IPFS beforehand.
Yeah, and then how does it define again the content type?
So the content type is going to be through like a JSON LD type of thing, but for now, like this data structure is slightly less, where it knows what the data definition is.
So do you do this when you upload it, or is this an automatic guessing mechanism?
When you add it to the object. Yeah. So when I do IPFS add, it constructs it.
So if I have an HTML file, then you say it's text HTML once I'm adding it to the object.
Oh, you mean the MIME type?
Yeah, the content type.
So the content type for the browser to render with
Because
so that's done with MIME sniffing on the browser on the HTTP server side. So
Just by file extension.
yeah, no, like they look. I think MIME sniffers look at the file extension and they look at the content and see like, oh, this is a JPEG. Here you go, JPEG.
they usually look at the first couple of bytes and because JPEG, PNG, zip, all those formats have a couple of magic bytes.
Yep.
So you don't even need to look at the whole piece of data, just at the first couple of bytes.
So to give you an example of that, so I should show you that basic thing. There's this image here that if we like look at it, it's this like nice, really big image of the tree, right? But if we IPFS ls.hash, we see that it has sublinks. So what happens if we like look at those? So
a file object can link to other stuff.
And if you do this, this one's probably not going to work because it doesn't have the JPEG headers. Hit down. But what you can do is you can screw with JPEG. So you can take this hash and say like this hash, which dumps out the JPEG. But I can do it into like JPEG, right? And then I can take like that again, and again, and then open foo.jpg. It's gonna have a header multiple times, so it's gonna freak out. It's probably not gonna show.
Oh, you wrote it the first one.
Yeah, it's only gonna do the first one. So let me do something slightly. Oh yeah, I understand what I did now. But let's say that I do the macro order. So and then I do it 3 times. And now, like weirdness. So if I then
Is this IPFS doing this segmentating the image, or
so when we add an object, if it's bigger than a certain size, we chunk it. So we have different chunking algorithms, and these are also configurable. Like,
and each file can have also links. So that's a
yes.
So it can either be shown as the content itself, and it can also link to other things.
Right. So you can request the actual data. So this is the object get part that I was showing you. So if we do IPFS, what was this last? So this is the last one. Let's say IPFS object get on this thing. It's going to show me just links to content and some metadata that tells it that they should be concatenated.
Mm-hmm.
So wait, is this the Unix FS structure?
Yeah. Okay. Yeah. So when you cat that thing, cat is like a Unix FS aware command that says, oh, a Unix FS file, cool. I'll concatenate all the pieces into one.
Can you scroll a little up from this file?
Yes.
So you start with that's the links. Okay, they point to different hashes.
Yep.
And what is the name tag?
The name is nothing on the Unix in those because you don't need a name. You know, they're just concatenated blocks. So you can actually have the same.
The name would be used in a directory for having the names of the subdirectories, for example.
Yeah.
But you're wrapping every object in this kind of format. Basically.
So in this case, yes.
You're gonna switch to hash splitting those, right?
Yes, we're gonna move to Raven fingerprinting based chunking. Is that what you mean?
I don't know. The term hash splitting is a term I've heard from like Bob and rsync.
Yes. So Bob uses ADLib32, I think. Or is that what rsync uses? Maybe rsync uses ADLib32.
rsync uses a not cryptographically secure hash.
Correct.
And attacking it.
Yeah. So it's like a super fast, like rolling thing. A long time ago, like basically pre-2000, David Naziris, we might know from Stellar, Kademlia, SFS, like a million things, came up with this thing called LDFS, the low bandwidth process, which he wrote because he was really annoyed that the network was doing stuff. And what it did was that it used rapid fingerprinting to chunk files in a better way than rsync, because he was sick and tired of rsync and things, so it was too slow for him. So he wrote this thing that uses actual content-based fingerprinting of the file itself to determine changes. So if I run it over a file now, and then I make some edits and run it over the file again, most of the content will be preserved because it's chunking based on the data itself.
That's what rsync is doing too.
rsync is doing so in just like a fixed size rolling window, and rapid fingerprinting is like a variable sized thing that depends on the content, like much more. Like, point is that the LBFS rapid fingerprinting was an improvement upon rsync.
Okay.
Yeah. You can I can show you like the actual paper that has the image because that like, makes it very clear where you have these chunk boundaries of different lengths, but the majority of them are preserved.
RABIN.
RABI, yeah. He's Rabbin has made a lot of really interesting contributions to it. This is like one of them. He didn't use it for chunking. That wasn't theirs. I don't think he did. He might. Cool. I want to try and graph the massive tree, although pulling it down by table map.
Oh,
So have it.
okay, yeah, I tried that and it took forever, and then I got something that didn't render.
Oh, really?
But I'm
Maybe it was like too big.
I think it will be like pretty massive, as like 60,000.
Let's explore it because we can explore it with the gateway.
Yeah.
So we took this database, or rather, Chris took this database, the GeoIP database, which is like this big description of mappings between IP addresses and their locations. So you can do like geolocation. This is basically how we do this part of like finding where people are. We use a GeoIP database, and instead of doing a request out to the rest of the network and getting a response for an API, Chris was like, let's just put it on IPFS. And so he took the entire database, made it into IPFS objects into like a really big tree, and then added it to IPFS so that when your node tries to find something, it calculates the right path and then fetches that, and then retrieves the result. So if you are connected to Chris and Chris is doing this, then he would look at your IP and from that determine a path through the tree, and then fetch an object, and then get a result. So it's a way of doing database queries through this.
And the object would contain location data.
Yeah, pretty cool. So the point here is like you can take these databases and open them up, right, and just put them on the network.
And how about speed? I mean, we saw like how fast it was fetching websites. That's because there's less peers. So if there would be more peers, would it be faster?
So it depends on the content, it depends on the access file, it depends on like the chunking. Like if it's a massive set of objects with tons of little pieces and very few people have them, then finding them might take a little bit longer. But you can obviate a lot of this by being smart when you like construct a graph and say like all of these objects should probably move together. And so when you define an application, you know all of the things that it points to, and you move it along.
Yeah, and for example, if you have a website with like let's say 20 files, does the amount of peers having this object will make it faster?
Yeah, so peer-to-peer systems generally.
So it will just like load files from this.
Well, it will load the DHC record. So unless those people have those files. So if you have a website with 20 peers, right, and you put it out there, and a lot of other people are viewing the website, then yes, because now a lot of people have the content, and then you would be pulling it from them. Yeah. But if only you have the content, then no.
Yeah. How to solve that incentive?
Right.
And how?
Oh, so this is a different set of protocols where IPFS governs how data is moved and gives you the policies that you can use to move it and decide how to like pin it or move it or advertise it and so on. And then you can find other protocols, right? So you can create a service that says, we are going to host your data for you, just give us what hashes you want us to pin and give us money for it. You could also right, so that's the thing. So IPFS has a sister project called Filecoin, which is around this, right? So Filecoin is a way of using cryptocurrency to incentivize storage. And this is about IPFS.
Yeah, I mean, we would do obviously that with Ethereum, but
yeah, so you do the same kind of structure where you reward people for maintaining content. Cool. Do you have any? The video. Oh, the video. The video is probably like more exciting to people. Or I'm just kind of bored. I like to start with. So check this out. So we can take the video and look at it on localhost. Video. So this is going to request a video and it's going to take a bit of time to like find it. There we go. So now it's going. And it's a little slow. Now it's playing. It just happens to be part of the game. So there you This is like Simple.
This is streaming now.
This is streaming from IPFS. And like streaming nicely, and it's pulling in the front as you would want it to, but you can also seek. And seeking is kind of like hang it for a little bit. Oh, that was nice. I don't, yeah, that was, yeah, that was nice. So sometimes when you seek, you have to find content. Normally you hear sound like a dragon screaming.
But why not?
Because, I don't know.
And you're connected to the
Yeah, something is weird.
How big is the network currently?
What?
How big is the network currently?
The network is pretty small right now because the people running, because it's the way you install IPFS is in the command line and you have to run it out and then explicitly run it, and we haven't made it really nice and easy to do this. The network varies from like the low end 60 to like 130 nodes that I've seen. It might go higher. I know there are other networks, so there are networks that are separate that don't talk to our network that run other things. So some other people are using it for stuff. Like some people build a YouTube-like clone thing, and it's actually pretty cool. Like you can upload video and store it on IPFS, and
Which one was
that's
that?
it. This was Together from like Paris, I think, and other people are doing somewhere.
Aerospace Industries.
And yeah, so you can, and IPFS happens to be integrated with this other player, which is pretty cool. Video. If I do playback, this will open is the playback video player, and it'll play this thing, and so now it's like playing here. And if you had a Chromecast, then it would show up here. You play it. It's pretty sweet. That's video. You can also run video through a website that happens to be running video. So if I take this thing here, it's a file. So it says like /play at the end. This is a website, so it's like some JavaScript. So like HTML JavaScript that will load whatever you pass it as an argument, and will load and play that video. So here it's going to play like this little path. And so here it's like loading this and playing it. So this was the video I was playing.
So this is the video tag.
Yeah. Yep. And it does range requests and all that kind of stuff for you.
And it looks in its own link object, or how? No, it just checks.
So right now, if you
it just checks the URL, right?
So it takes the hash. So at the top, it takes like another hash.
You added a hash.
I can make it bigger. So there's a URL with like a hash at the end. So.
Right. Okay.
By the way, hashes. You don't have to have hashes in the naming. Like you can actually have pretty URLs. It's a long discussion. So.
Yeah, that's actually something we would like to know how you do that. So pretty URLs means
having like a nice name resolver that points to content.
Yeah. So how would you do that?
So this introduces the naming system, which is based on identities, and so you can have. Suppose we have a key space, right? So you have a bunch of keys. Suppose that you add to the routing system, so the DHC, an entry that creates a mapping from one key to a value. So think of this kind of like a get branch, like saying master is at 0, 3, A, B, C, D, or like master is at E, F, 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 right? So you can create these records that make that pointer and dump them into the DHC. And what they're mapping is they're mapping the hash buffer key to another value. And that other value is just a path, any path. And so what happens is if you can a link like, let me illustrate this. So you can take a link like this and publish. So I can take like my local key. So here it gives me like my own the hash of my local key. So I can do IPNS that. And that means that I will create a record that points from this one, I'm going to abbreviate it so that it's trivial. From that one to this. So when I publish name, it's going to create a mapping like that. And when people request this is still a hash, right? So it's still ugly. But it means that when people request this, they're going to get that mapping. And if I create a new mapping that points to some other thing, like maybe like 2 or something, that they can resolve that in the future and get a mutated version. Does that kind of make sense? And then I can sign those records with like a private key, so then they can certify that it was really me that did that. So that's a PKI-based naming. On that, you layer pre-names, which is you can do with DNS or with any other name resolver. And so with DNS, we have text records. So if I dig, I think
So this is the same DHT that's used for locating the immutable pieces, right?
this is the same DHT.
There's just one DHT, and so you're putting the IPNS stuff and the piece locations in it.
Yes.
I'm going to ask a sort of naive question. I have a vague understanding of how Gamma DHTs work, but it seems like you have a really large number of pieces, like many times the size of the network, say, which would be easy to do if you upload a file system to it. Don't you need to talk to like all the nodes to publish that?
No, you publish to a constant number of nodes.
And then they relay that to the
So each object you publish to a constant number of nodes. They're different. So you'll be publishing to a different set of people every time you publish.
So if you have a big enough number of objects, it seems like you should touch the whole DHT eventually.
So yes, if you have a big number of objects, not the DHT, only your routing table. So in Canada, you build a routing table with this log to whatever the number does, and from that routing table, you store it to people. So if that routing table is big enough, you don't need to store it. Which means that somebody will find it as they walk through the DHT.
So you have a fixed node ID on your laptop that will be the same when you go to your next destination after this place. And so the nodes all know your IP address is this right now, where you nicely punched through the map. And the next place maybe you will also, and so you'll probably your new IP.
Yeah.
This is sort of a privacy disaster that you just.
Yeah, this is why I'm saying that the DHT are not good for privacy.
Yeah.
Particularly when you share addresses.
Yeah.
You can do a DHT where you share content but not addresses. And you can do different policies.
Right. But if there's like several pieces of content that only you have the context to identify.
Yeah, so this is, again, some content you may not want to advertise, period.
Right, but maybe there's content you do want to advertise, but there's only a few people that have it. You want to advertise.
Yeah, so what I basically tell people is like, don't use DHTs when you care about preserving privacy.
Right.
Use a routing system that's designed for privacy. Meaning that when you're resolving a query or like advertising something, you're doing so taking privacy into account. So that when you do it on the routing system, you're not leaking addresses, you're not leaking who you are, and so on. And there are ways to do that, right? Like you have like secret sharing systems and that kind of stuff. So you can get to doing a routing system that is anonymous for moving around content.
Well, there's certainly some ideas about how to. I'm not sure any of them are.
Well, so there are like really cool cryptographic constructions where you have a network of peers and people say something and they encrypt it and it gets shared to the network in such a way that people can't tell who said it originally. And so then in the next round, the person puts the content into that and then it gets re-encrypted and moved around. And then people think, voila, they have a thing. So there are ways of doing that. That's not like our main focus. Our main focus is to get things to be really fast. There are strong uses for those kinds of routing systems, and we do care about building them. But it's like it has to be done specifically for privacy.
And it's really hard. It's incredibly difficult, like code-wise and implementation-wise, like design-wise, to try and work with both these problems at the same time. Like
Right.
taking this and then this is really useful, and then right now when we open our browsers, there's 10, 30 tabs open, and You just fingerprinted yourself right there. So you take your computer, you go to a cafe somewhere else, and you open all those tabs again,
Well,
and boom.
I mean, I don't, but most people do, yeah.
Yeah, I did. I'm starting to.
Yeah. Yeah, like I actually, so after a long time thinking about privacy and so on, I am no longer convinced that you can actually have privacy unless you work extremely hard for it.
That is really, really disappointing to hear because I think that the content readability is absolutely essential, and you've got the best shot at it right now. So I'm very.
No, so I don't know.
Hearing that you.
Sorry. Let me qualify what I know about. Given the web as it is today, so the way that people use HTTP today, and the way that people use websites today, and the way that people use DNS today, and the way that people use route traffic and the CA system, and all of that, given that, there's not you can't get that system to give you privacy unless you work extremely hard for it. Meaning that like you, from scratch, like the computer is like going to be privacy, and like that's it. You don't like touch anything else.
I agree we have a long way to go, but I think that when you are starting from scratch, as you're doing, doing it with a sort of this is futile sort of.
No. I don't mean to say this is futile given all systems. I'm saying this is futile given the current system, so we need to move to new ones.
But
I'm making a point for moving in this direction. Yeah. So saying that this is better for this can be better for privacy depending on the routing system. Like I was saying, all of those concerns are saved down into the routing system. That is the only thing that leaks information, right? So you can just replace that entire piece with something else.
I have to take my computer off. Yeah. So if you want to say something, something important, if you want to finish it off.
Something important. I don't know. Well, we should. Yeah, something important is this: the following. As we go about making what the new web is going to be, is really important to not fragment it. So when the web was originally created, there were a whole bunch of different hypertext protocols. And what made the web strong was that Tim Berners-Lee said, no, we're going to have one protocol and we're going to link them all together and it's all going to be nice. Like you're going to reach any one server is going to go to any other server. And if you want to run a different protocol, like not HTTP, that's cool too. And like we'll make space for it. And you have links that point to different protocols. And like he did all of this work to make that happen. And that's what gave us the web as it is today, where it is one place that we can link to from anything and so on. As we go about making the new set of systems, it is important that we preserve that we preserve linkability from the current web as it is, that we allow to some degree linkability to the old web, or like the today web, and that all of these systems have a common way of addressing things, both in terms of content and identity. And that is what's going to make all our tools be able to interoperate in terms of being able to generate graphs of it, being able to replicate it, being able to like make sense of the content, all that sort of stuff. There's no need to like create multiple different versions of it. We should unify that because that's what will allow all these systems to be much stronger. That's the important thing to say. Cool.
Nice. Thanks.
Any other questions? Do you guys want to say something? Like you're here? I feel like I just like said things that you have known for like a long time. So did you want to talk about your like data structure?
My data structure. Which one of them?
Anyone. I don't know if you have.
I haven't prepared really. I mean, as you said, like the cool thing with having like the data firsthand is that you can actually make data instead of like using a database which has like structures and indexes for like everything you're supposed to be wanting to do with it. You can like directly like roll your own, and like for the GeoIP stuff, it's basically just like it's basically just a B tree. So you take your, if you want to look it up, you take your IP address, convert it to integer, and then you get the root node, which has like two numbers. Like first is like 0 or 1, I think in this case, for some reason, and the one is there's like roughly along halfway of the available IP space or the mapped out IP space. And then like you see, is it larger than this or not? And then you pick a branch and you get a new node, which also like has multiple children. You find the right one, and then you like recursion this, and suddenly end up with the leaf which has the data you wanted. So like it's like the JavaScript, but this is just like a few lines actually to get and look at this structure. And yeah, and you can do like other things, and you have to do a bit more like kind of a bit more work. But I mean, I guess there will be libraries for this as well. But you can get like really down with kind of actual data that you're using, instead of abstracting it away in a database that is you usually don't understand completely anyway. Yeah, I find it pretty good.
It's pretty sweet. Like we have the entire IP database, or QRP database in IPFS, and nodes just do like one query for the path and find it. So normally databases are written this way, where like your database is going to be smart. It's going to have its own data structure, its own layout on disk, and it's going to do an access pattern. We're just taking that and putting it on the web.
What do you call the DAG, the data structure on the client that stores information about content that it knows about?
Yeah, so that used to be called, so that is called like the repo.
For database?
Yeah, so we call it a repo, like a repository.
Yeah.
So IPFS every IPFS node has a repository, a local repository of objects.
Yeah.
And some of those objects describe like pins and all that kind of stuff.
So is that, is data, I don't know the proper data structure term, but is that a tree or a database? I don't know, or a graph.
It's a directed graph. So it's like a tree, but
It's one way.
yeah, because of the hashes. So all Merkle trees are a DAG, where it points in one way.
And the DAG is specifically one way.
Yeah, so Merkle tree is really a misnomer in that it's really a DAG.
Yeah.
But the reason it was called Merkle tree is because Merkle was using it to do this really nice balanced thing. With like, you had like the like, he was doing like signatures, right? So he was revealing like a path through the tree. So he was creating a hash tree where like a binary balanced hash tree. And so he was revealing a path through the path. And so that's where Merkle trees come from. But you can throw away that use case for this and say, instead, we're going to use the nodes in between to have data as well. Like Git. Git does this. Git is a Merkle tree. But it's not a proper Merkle tree. It's like a different
Are there
Merkle tree.
limitations on branches?
Nope.
So it could be, you can have a million of trees.
Yep. So what you do in that case is that the node will shard, like instead of having one massive object, you will shard the node and say it's like a union node. We haven't implemented that, but we can. It's not difficult. It's just a way of specifying like, keep looking in this other place. Kind of like what a file system does. A file system is also a graph. It's just that it is on the disk.
Yeah. So Ethereum is just a DAG over time.
Yep. So you could in fact, now that the chain is available, I could go and import the entire chain into IPFS and make it extensible.
Yeah, the block number is just the time.
There you go. Cool.
Yeah.
So yeah. So you could run a script that just imports it every once in a while, or like an Ethereum node that receives the latest blocks and just imports them.
Yeah. Yeah.
Anyway, cool. Sweet.
Nice, thanks.
Sounds good. Thank you. I feel like I bored both of you terribly.
Yeah.
Saying the same things like, oh, I heard this a million times.